All right, let's get started. Welcome, everybody. So it's a pleasure to welcome our speaker today. It's Alex Sisto from Heriot-Watt University, and he's going to tell us something about extra large Artin groups and why they are hierarchically hyperbolic.
All right, thank you very much. Thanks for having me. So I'm gonna talk about well, two papers. One is joint with Jason Berstock, Mark Hagen, and Alexander Martin, and the other one is joint only with Hagen and Martin. And it's about, I mean, at the very end we will get to Artin groups and extra large types Artin groups, but I will start from this hierarchically hyperbolic business, and so the plan is starts with what is, from now on I will shorten everything to HH. So what is a hierarchically hyperbolic space, HHS? And this is a notion that we defined back in 2014, and when we were kind of trying to come up with this notion, I said this thing that's written here in the top right, and you will see why it's funny in about half an hour. So after if you have seen me give talks about hierarchical hyperbolic spaces and groups before, you will have seen some version of this part one. I will make it a little bit shorter, but I will change, let's say, the working example that I used to make it as similar as possible to the extra large Artin groups that I want to get to at the end. So at the end of part one of the talk, it will be very clear that you don't want to check directly if something is an HHS. So you don't like that. That's just, you will see, it will be clear why. It just seems way too complicated. So part two, I will show you a criterion for showing that something is an HHS. So it's simpler. So that one, I will not give the full definition of HHS, but I will give you the full criterion, or a full criterion for it. And then I will get to this Artin groups and basically saying a few words why the criterion applies. Very good. So part one, what is an HHS? Let me start with a list of examples which I pre-wrote here. Okay, so this is a notion which is supposed to generalize hyperbolic spaces and groups. And also, if you have a direct product of hierarchical hyperbolic spaces, you're still hierarchically hyperbolic. And if you're hyperbolic relative to hierarchical hyperbolic spaces, you're also relatively hyperbolic. But now, okay, this is kind of the basic examples. Then we get to maybe the motivating examples, which are mapping class groups and cat zero cube complexes, at least many of them. So basically, the notion was defined in order to treat these two cases in a common framework. So that was the original idea. But then there's many other examples, lots of fundamental groups of three manifolds. And then in the last maybe year or so, there's more additions to the list have been made. So if you mod out large powers of Dane twist in the mapping class group, you get an HHS, XL Artin groups. Well, that's what we're going to talk about today. And also certain extensions of Beach groups and curve stabilizes, other things related to mapping class groups. And all these examples down here follow from the criterion that I will be, have been first shown to be HHSs using the criterion that I will discuss in the second part of the talk. Okay, so there's hopefully you're interested in at least some of the groups in this list, or groups and spaces in this list. And the good thing is that this notion gives you a good control on the coarse geometry of these spaces. And it allows you to prove various things, such as that quadratic Dane function, finite asymptotic dimension, results on quasi-flats, which then in some cases can be used to prove quasi-geometric rigidity, universal cylindrical actions, uniform exponential growth under suitable conditions, semi-hyperbolicity, solvable conjugacy problem, lots of things. Okay. And yeah, there would be too many people to mention to cover all of these. So I think I will mention only the people that don't have a permanent position. So I think there's Russell Spriano for this and others, and then there's Soda and Petit here, Russell again. I'm probably missing someone, for sure I'm missing someone. Very good. Excellent. So, all right. So hopefully this motivates you to at least try to see what this notion is about. There's a good list of examples and a good list of theorems. So roughly, so let's do the one sentence description. A hierarchical hyperbolic structure on a metric space is some kind of coordinate system where the coordinates take values in hyperbolic spaces in the sense of ground. So shall I say a few words about hyperbolic spaces? I've been told I'm not. Should I or should I not?
I don't know. It's up to you. I mean, I think most people here know. So I mean, you can draw like a small picture.
All right. Okay. 1 minute on hyperbolic spaces. So geodesic. So some space where you have a notion of shortest path, which is geodesics. Metric space is hyperbolic if there exists some constant delta, such that for all geodesic triangles, and then I will draw the rest of the definition. So you have a geodesic triangle like so. You have a point on one side. So geodesic triangle is just three geodesics that pairwise share the endpoints. And the condition is very simple. So every point on one side is within delta of a point on the union of the other two sides. So maybe a better picture would be the triangles look kind of like this. Oops. And I think that if you keep in mind the following two examples, R and trees, you're doing pretty good. For they will actually cover the working example that I'm going to use in a second. So here's a tree. And also there would be like real hyperbolic spaces and many more. And I mean, the point is that it might look like a strange property, but if you have never seen it before, but there's the geometry, the large scale geometry of these spaces is not that hard to understand. Like there's lots of things that you can do and play around just with this very simple property. Okay, not going to say anything more. I'm going to get back to this. So the coordinate system with values in hyperbolic spaces. Very good. And to explain what that means, I'm going to have a working example, which is the right angle Artin group, if you know what that means, on a path of length 3. That is to say, G is the group. So if you don't know what right angle Artin groups are, I just give you directly the presentation. So A, B, C, D. So it's generated by four letters, and A commutes with B, B commutes with C, and C commutes with D. And those are the relations. And in particular, if you think about it, G, well, or if you look at the defining graph of the Artin group and you're familiar with that, G will contain two copies of free group on two generators cross Z square, which are suggested here. So they're generated by A, B, and C, and B, C, and D. And they share a Z square, and actually the group G is the amalgamated product of these two. Okay, so it's a particular group that splits as F2 cross Z, amalgamated over Z square with F2 cross Z. Okay, so that's the working example, and it will have similar features to the more complicated extra large Artin groups that I'm going to talk about later. So okay, coordinate system with values in hyperbolic spaces. So I have to tell you what the hyperbolic spaces are, at least. So what are the hyperbolic spaces? We'll denote them. So there's going to be this family of hyperbolic spaces that provides the coordinates. And there are three types. So there's type 1. One is the Basser tree. So I'm going to call T. So it's a tree. In particular, it's hyperbolic. And the vertices of this tree are the various cosets in G of this F2 cross Z, and the edges correspond to cosets that intersect. Okay, very good. So here's one. This is not enough to understand completely the geometry of this group. You lose a lot of the information. This tree knows nothing about the F2 cross Z's. So you need more. You need more spaces to have a decent coordinate system. And you will have a copy of Z for each coset of F2 cross Z. Okay, that's something reasonable. And then maybe you're expecting an F2 also for each coset of F2 cross Z, but it's actually a cond of F2, where you con off certain copies of Z, but you can forget about this cond of. Yeah. So don't worry too much about this if it's unclear. So in any case, hopefully it makes sense that if you know where a point lies above the Basser tree, you know where it lies on the which height, let's say, it lies on this F2 cross Z, and where it lies on the F2, then you can reconstruct where the point is. So hopefully that makes sense. And one thing that I'm not going to explain so much is that there exist natural maps, which I'm going to denote pi y, from G to each of these hyperbolic spaces, because it doesn't really matter how they're constructed. I'm not going to use it. I'm just going to use that there are maps. So the map to the bus R3, I guess you can see right away. So you map across it to the corresponding vertex. The others are a bit more complicated. Okay, and so these maps are what allow me to compare the geometric features of G with those of the various hyperbolic spaces. So that's, yeah. And they are the coordinate maps that I was mentioning before. And the study of the geometry of G, the coarse geometry of G at least, can be reduced to the study of the geometry of these hyperbolic spaces. And there's various ways in which this happens. Let me mention one, so maybe the most prominent one. Oops, theorem, or well, I guess in this case more proposition, but okay. So the distance formula. Okay, so the distance formula, I'll write the quantifiers here in a second. Let me just first write things with constants. So what does the distance formula say? So you have 2 points in your group, and you want to compare and you want to study their distance in a fixed word metric, which is dg. Okay, so if it was the usual coordinate system on Rn, you would say that that up to multiplicative and additive constants, this is the same as the sum over all coordinates of the distance in that coordinate. Okay. So pi y x, pi y y. So again, if you had R2, okay, which is an HHS by the way, and you have 2 points, how do you compute the distance? You project it to the 2 spaces. And then if you only care about the distance in up to multiplicative error, you just sum the distance in the two coordinates. Okay, maybe just an aside. Okay, and right, so this formula is almost correct. If I write it like this, this sum could be infinite. So I'm going to introduce this symbol, which means just take the values that are above a certain threshold and ignore everything else. Okay, and that's the formula with quantifiers that for every sufficiently large threshold, there exists multiplicative and additive constants hidden in this symbol, so that for every 2 points in the group, you have this.
Can I ask a question?
Yep.
For each L, there exists K and C, right?
Yep.
Do we know how do the K and C depend on L? Like, do they depend linearly, quadratically? Is there like a closed form for how the K and C depend?
Yeah. So there's some study of how they depend in the case of the mapping class group, and I don't remember, except I mean, the only thing I remember is that it was pretty bad, like some exponential involved. In general, yeah. So there's I forgot who was doing it. It's so maybe if you Google like effective distance formula or something like this, you might find the paper that I have in mind.
Thank you.
Sure. Okay. Very good. So this is one. Okay. So hopefully clear what this means, and it's one way in which the geometry of the various hyperbolic spaces controls the geometry of G. Right, and maybe more inspired by this example that we've seen of this amalgamated product. So there's a bus R3, and for each point there's a product of 2 hyperbolic spaces essentially, which is associated to it. And there's another rough description. So again, roughly. So here's another informal description of what an HHS is. So it's an inductive definition, I mean, an inductive, I don't know, heuristic, let's say. So hierarchical hyperbolic spaces include hyperbolic spaces, products of simpler hierarchical hyperbolic spaces. Okay, right, and you should think of Z and F2. Okay, so products of HHSs, so maybe F2 cross Z. And then the one that's informal is hyperbolic arrangements, is one way of describing it. Of HHSs. So what this is supposed to hint at is that in our case we have a Basser tree. So we have a tree which encodes how this simpler HHSs interact. And so if you want your group, our group G is a union of simpler HHSs arranged in a way that's encoded in a hyperbolic space. I don't actually know how to make this this precise, but as heuristic, I think it's useful. And maybe maybe I already told you enough to so that you, if you have a space that you're thinking about that you understand very well, you might have an idea whether it could be an HHS or not, hopefully. And right, so I'm not going to say more about what an HHS is, and the reason is that there is an unfortunate feature of the definition, which is I'm going to just show you now the definition. So this is the definition, or at least the first version of the definition got streamlined a bit, just a little bit. And so this is the definition. Yeah, it's I mean, it is what it is. I mean, I've seen shorter definitions. And so while maybe hopefully with the heuristic I've given you, you can have a rough idea of what an HHS looks like and whether your favorite space is an HHS. It would be very understandable if you didn't want to go and read the definition and figure out if if it applies to your case, which is to say that part 2, you really want to have a much simpler criterion than checking the definition. Okay, and now I'm gonna, so before showing you the criterion, I would like to show you what it is inspired by. Only for those of you who know the curve graph, though. I don't think it's worth kind of talking about that, like introducing it too much just to use it as a motivating example for something. So okay, so if you don't know what the curve graph is, you can I don't know, take a break, go grab a coffee, or I don't know, reply to emails, whatever you want. So the criterion is by curve graph. Okay, so only a few minutes, so don't worry. So the hierarchical hyperbolic structure on mapping class groups so what are the curve graphs in that case? So what are the hyperbolic spaces in that case? They're curve graphs of subsurfaces. Of your given surface. And the point is that okay, you have all the various curve graphs of all the various subsurfaces. However, the curve graph of the, let's say, it's mapping class group of S. So the curve graph of like the main curve graph actually does contain all the other curve graphs except annuli, because annuli are always a pain, and I don't want to talk about them ever again. So they contain, it contains all other curve graphs as what? As links of vertices or simplices. So for example, the curve graph of a surface minus a curve is the link in the curve graph of S of, you know, that curve, or the vertex representing that curve. Right, so you have your surface here, and maybe this is gamma, and then all the curves disjoint from gamma are, you know, that which would be this. You can think of them as curves on S minus gamma. Okay, all good? No, it's a lie. Okay, so it's a small lie, because the curve graph of one's puncture tori and for all spheres as well have adjacency defined differently. So it's not disjoint curves, but it is curves that intersect minimally. So that is to say that if you look at right, that you will have links that whose vertex set coincides with the vertex set of the curve graph of one old torus, but it won't be isomorph. You know, it won't be the same graph. Okay, so this leads to the following definition. So this thing of missing edges. So it's basically, the point is that so what we want to do is encode this fact that the curve graph contains all the information that you need, or at least all the hyperbolic spaces that you need to give the HHS structure on the mapping class group. But you need that there's some missing edge type of issue, which is corrected by the following definition. Okay, so I'm done talking about the curve graph in case in case you got distracted doing something else. Now back to, you know, the core of the talk, let's say. So here's the definition. You have a group acting on a simplicial complex, let's say, or just a graph would be fine, but yeah, let's say simplicial complex. So then Y is G hyperbolic. So if maybe it's disconnected and everything, but I make it hyperbolic, it could even be discrete. So if it becomes hyperbolic after, so by adding finitely many orbits of edges, G orbits of edges. So basically, this is also how you construct Cayley graphs. You have G acting on itself, considers a discrete space. And yeah, and then you add finitely many orbits of edges in a way that makes it connected. Very good. And this is the only definition I need for the criterion. And now I can show it to you. And here it is. Here's the criterion. Okay, it's much like that. That's all. That is all. So it starts here and ends here. So maybe it's you know, not 2 lines, but it's a manageable size, and I'm gonna explain it a bit. But first, let me highlight the main features of it. So you have a group G acting on a simplicial complex X, and the main requirement is that links of simplices are hyperbolic. Okay, so if you can if you want, you can just stop here. Like this is a good level of understanding of this statement. You want a group, for example, a mapping class group, acting on a simplicial complex X, the curve complex, and links of simplices are hyperbolic. So, but I don't want to cheat, so I'm actually gonna explain all the various parts of this definition. Very good. So, so the action is co-compact, fine, and stabilizers of maximal simplices are finite. I don't think that these two conditions need further explanation. Okay, so links are, I said they're hyperbolic, but yeah, so you have this issue that you will always have disconnected links if you take. So, for example, if the complex is dimension 2 and you take an edge, then the link of that edge will be disconnected. Let's draw a little bit of the link of an edge. So certainly not hyperbolic because it's disconnected.
Sorry, what is hyperbolic here? The link or the stabilizer of the link? Because you have something else.
So right. So the link is, and now this is the notion that I defined in the other that I defined before, stabilizer of the link hyperbolic. So maybe I'm allowed to add edges. So finitely many orbits of edges where the orbits are with respect to the stabilizer of the link. Okay, so the stabilizer of the link is very much related in the mapping class group to the mapping class group of the subsurface of a certain subsurface, and I can add finitely many edges.
Sorry, I'm still confused. What is hyperbolic here? Could you say again? I'm sort of lost.
So you take the link.
Yes.
Okay. And then you and then you add finitely many. So possibly you have to add finitely many sub-link delta orbits of edges to the link, but then you get something hyperbolic.
Okay.
Okay. Yeah. So there's this unfortunate little technical thing, but mostly in view of condition C, which actually maybe I'm gonna describe now. So certainly you have disconnected links. For example, if you take a codimension 1 face in a maximal simplex, then its link will be just discrete. Okay. So, and condition C says that if that's not the case, then you get something connected. So in fact, except in this particular case, the link will already be hyperbolic. Okay, very good. So the second part is a bit funny, but I don't know. It is what it is. So it is. So this link is quasi-symmetrically embedded in a certain funny space, for which, I mean, if you don't have much intuition for what that means, for what that is, don't worry, because I don't either. This is maybe the more mysterious part of the definition, and well, but okay, there's a certain space which is contained in a certain other space, and those are Q embedded. Okay, so for all simplices, and then finally, the only condition that I haven't mentioned yet is, let's say, it's a local combinatorial condition. So this is entirely combinatorial condition. So what we wanted to say is that the link an intersection of two links is the link of another simplex. So if you write it like this, then the curve graph doesn't satisfy that condition. So you make it a little bit more complicated. So the link of a certain simplex is not just quite the link of a simplex that contains, say, delta. So this is supposed to be the join. Okay, so this is just a simplex containing delta. So it is the link of this simplex containing delta, and then it's joined with something else. So you, at first approximation, you can just think that intersection of links is a link, and it's just slightly more technical than that. Okay. And once again, let me remove all that is inessential. Just a group acts on a simplicial complex and links are hyperbolic. And the conclusion is that the group is hierarchically hyperbolic. Okay, that's it. It really fits in this slide. And I mean, it's a little bit technical, but I decided to actually show it to you in its full form, just to, to prove to you that I'm not cheating. It's here, like that. This is it, and this is and this in this special particular form is exactly what we used for mapping class groups mod out powers of Dainquist. There's a slightly more general version of the criterion, which covers the other cases. Are there questions on this statement or? Okay, so if not, right. So note there exists a slightly more general version, which you might need. It's same style, but that exact version actually is used to cover this at least one example, but it will not be exactly the one that's needed for Artin groups, even though it just barely fails that particular one. And I mean, the more general version is just slightly more technical. It's not really, it doesn't really have additional complications. Very good. With this in mind, groups acting on simplicial complexes with hyperbolic links, we can move on to Artin groups. But first, let's do our simpler Artin group, the working example from above. So recall our G, which was the rectangle Artin group on this, and which has a particular amalgamated product decomposition, which looks like this. Oops. Okay. And we want our hyperbolic spaces to be T, some Z's, and some condoff, and forget about condoff, F2s. And now, what is this mysterious hyperbolic this mysterious simplicial complex from the criterion? So what's X from the criterion? So we want, again, what do we want? We want a simplicial complex whose links are these spaces. Okay, and the first attempt would be to say, okay, I don't know, we have a hyperbolic space with decent combinatorics. Let's try to take it. So T. T was the buster tree, if you remember. Okay, so let's see what links of simplices are in the buster tree. So I was allowing the empty simplex. Maybe I didn't say it, but I was allowing it. So the link of the empty simplex is the whole space. And so we have one of the three spaces that we wanted. That's good. Then what else is there? Well, there's the link of just a vertex. Okay. So what's the link of a vertex? Well, it is discrete. So it is discrete, but that was expected. We knew that we were gonna get some discrete links. But if you think about it, these various points in the link all correspond to a certain coset of a z square inside f2 cross z. And if you think about it a little bit more, you will see that, or hopefully it will make sense that as with this kind of strange notion of adding edges, this is qi to the cond of f2s. So it's some z square cosets in f2 cross z. If you cone them off, you know that the cross z direction doesn't do anything, and it's basically like coning off an f2, if that makes any sense. And if not, just believe me, you get these types of links that we were looking for. So type 1 and type 3 are, we have them as links for this x equals to t, but we don't have the z's. So that's not enough. That's not the correct space. It's not the correct x. But there's a solution to this, which is we make x just the buster tree just slightly more complicated. And so the solution is to play a Squid Game. And so the game is to replace each vertex of the buster tree by a picture which looks like this. Okay, so that's a squid. That's what they refer to as a squid, and we were referring to them as squids well before the TV series was out. So this picture, which seems silly, so okay, so the vertices, the tentacles are in correspondence with a z. So this picture might look silly, but it's important. Like basically this picture of the squid is used in, okay, so in all these examples, so this, and this, and even there's something here. There's a distinction between hierarchical hyperbolic space and hierarchical hyperbolic group. There's in work in progress, we're clarifying that, and also in here. So the squids are used in 4 out of 5 of the applications of the criterion. Okay, so maybe another picture to clarify what I mean. So here's a bit of the buster tree, and then you replace in a suitable way each of the vertices with a squid. And I didn't say how you connect the squids, but you connect everything to everything for squids corresponding to vertices that were connected in the tree. Okay, is this clear? I hope so.
More or less.
Okay. So in any case, you start with the positive 3 and you replace each by something like this. I didn't quite tell you exactly what the tentacles are in one-to-one correspondence with. So in this case, I am cheating slightly, but not too much. So the point is that now, again, what do we want? We want links that are quasi-symmetric to the correct types of links. So if you think about it a little bit, you will see that you have in this this new simplicial complex, or you have links that are quasi-symmetric to the old links, to old ones. I mean, meaning to links for T. So the two types of simplices that of links that we had above, we also have here up to quasi-symmetry. There will be lots of bounded. So that's good. We have lots of bounded links, but that's not a problem actually. So bounded. Okay, it's geometric group theory. Bounded spaces don't count, so that's okay. And then basically what we force is to have the Z's as links. So in particular, as links of so you take one squid. So a tentacle of a squid, and then connect it with the head of the other squid, and then the link of this is the Z. By the way I constructed the graph. Okay. So it's a funny little construction, but it works. And yeah, so for that particular example, you have a simplicial complex which looks like this, which actually encodes the whole HHS structure of this particular group, and you can apply this this criterion to it. Okay, that was let's say a warm-up for extra large type Artin groups, which is the last thing I'm going to talk about. Okay, we now just discuss those. So Excel type or Excel large Artin groups. So first of all, what is an Artin group? So you start with a label graph. Okay, so you have ST, and then you have some integers, some positive integers as labels, MST. At least 2, I guess. Yeah. Okay, and you make a presentation out of it. So you look at the group generated by the vertices, and then there's this funny relation that if you do ST, 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 and so on, MST times, then this is the same as doing TS, TS, and so on, MST times. So for example, if MST is 3, then you have actually STS equals TST. While if you had MST equals to 2, you would have just a commutation. So these groups are interesting because, for example, they include right-angle Artin groups when you have only labels 2, and it also includes braid groups. And also they're related to Coxeter groups, because if you add the relation that every generator squares to 1, you get Coxeter groups. And okay, the theorem with Mark Hagen, Alexander Martin, myself is that, oh yeah, I forgot to say, so before the theorem, the XL means that all MST are at least 4. We can do something a bit more general, but let's not bother with that. And then the theorem is that XL Artin groups are HHGs. Very good. So there are right-angle Artin groups are HHGs. Now extra large type Artin groups are HHGs. I'm definitely not an expert in Artin groups by any stretch of the imagination. As far as I know, all Artin groups could be HHGs. Wait, I don't know. Maybe not. Who knows? We'll find out. But it's really hard to do something for every Artin groups. There's very few theorems about all Artin groups. It's always about some particular class, or almost always. Very good. So, but okay, regardless of where these groups come from, let's try to understand why they might be HHGs, and that's maybe like let's say an instructive I don't know, heuristics discussion on how you might try to figure out if your favorite group is an HHG. So, okay, what was this HHS structure again? It was a coordinate system with values in hyperbolic spaces. So if the group was hyperbolic itself, we could just use one coordinate. We could just use the group itself. So we have to understand, okay, so the group is not going to be hyperbolic, but let's try to understand why it's not hyperbolic. So that should tell us something about what we expect the HHS structure to look like. And so a good way to do it is to hunt for subgroups that are direct products.
Sorry, what is H? So what is large exactly?
So large is MST are all at least 3. Yeah.
Uh-huh.
Yeah. So and actually
and extra large.
All coefficients are at least 4.
At least so it's 4. Okay. Mm-hmm.
Yeah. So for example, it could be this. This is an HHG. Yeah.
Mm-hmm.
So the full theorem is actually that if you have a large Artin group and if you sum 1 over MST over the size of a triangle, you get something strictly less than 1. So for example, also this would be fine. But we are not allowing coefficients equal to 2. Even though that, okay, let's not get into this technical thing. So there are a bit more general versions of this and a bit even more general conjectural versions, but in any case, they wouldn't cover all Artin groups anyway. But yeah, it might be interesting to look at in the future, but we ran out of, we decided to call it a day when we got to here for now. So, okay, so I was going to say, you have a group, you want to understand its non-hyperbolic behavior, so you might want to look for subgroups that are direct products. And you ask some experts in Artin groups because you don't really understand them very well or at all, like me. And then they will tell you, well, okay, so if you take a generator, so I know that the centralizer of a standard generator is gonna be a free product cross Z. Okay, so very good. We have to keep this into account. And this is, as far as I know, this was first observed by Martin and Pshitinsky. I'm not really sure if, yeah, so it's definitely in their paper. Not sure if it was observed before. Okay, so and then you ask the expert, is that all? And the expert will tell you, well, not quite. There's a bit more. So if you have an edge, so they will tell you, if you have an edge, then these two generators, S and T, will generate something which is an Artin group. Let's call that a hydral Artin group. And this is almost a product, so it's virtually also an Fn cross Z. And more specifically, it is a central extension, of a virtually free group. So the center of the central extension is Z, which is ZST, generated by some particular explicit element, which is called ZST, but I'm almost running out of time. Okay, then again, inspired by the Basser tree for the other example, you might say, well, okay, let's make a graph where the vertices are cosets of these things, and then the edges correspond to these vertices interacting. And yeah, and indeed, you can phrase it a bit differently, in more algebraic terms. So you can consider all the subgroups generated by standard generators and by these particular central elements, and make what makes sense to call the commutation graph. So YH, where the vertices are cosets of the normalizers of these things. So the normalizers and centralizers coincide in this case. So the normalizer of these things are the things that are actual products or related to products. Okay. So far very similar to the Basser tree example. And then edges are defined in terms of commutation, actually. So there's an edge between G and H and H prime. If G inverse and H prime H inverse commute. Okay, so in this algebraic gadget, so I'll conclude. I'll only need a minute. So various facts about this gadget is that one is hyperbolic. And actually the work was already done by Martin and Chitysky, because in their paper, they construct a certain cat-1 complex, and which is quasi-symmetric to this commutation graph, and that's how we know that it's hyperbolic. So this is not a tree, but it has no triangles or squares, which helps with the combinatorial parts of the definition of the criterion. And finally, last thing I'm going to say, the criterion again applies not quite to this. So this is kind of an analog of the Basser tree, but to let's say to the squidification of this thing. And that's all. Thank you very much for your attention.
All right. Thank you, Alex. Thank you. Okay. So if there are any questions to the speaker, you're welcome to ask them. So in this construction, I mean, in the application, so how important was it to the Artin groups? Where was it important that they were extra large type?
Okay. So one essential thing is that this cat-1 complex okay, so this works if whenever you have a triangle. Okay, so STU 1 over MST plus 1 over MU plus 1. Oh, sorry, UT, MUS. Anyway, so the inverse of the coefficients is less than 1.
Mhm.
Okay. So that's one thing. So if we don't have that, we have not. I mean, we just don't even know where to start. It is possible that that this outline works under with this hypothesis, but having edges label 2 is surprisingly annoying. So basically, it's only for technical reasons. I mean, so on one hand, it's only for technical reasons. On the other hand, I think it requires actually significant additional work to have this this edges label 2. Basically, all lemmas, we have a series of lemmas that all split in two, that they, instead of having one case, they have two cases, and it's but okay, but this so it should work. So I believe it should work in this setup because we have this cut minus 1 complex by Martam-Shititsky. And if you don't have that, then I don't even know where to start, but maybe, yeah, maybe there's other methods.
Another question I had, I was trying to remember, I think there is some other notion, whatever is called being sort of HHS or whatever in some relative sense, right? You know, being relatively, what
Yeah.
is it called?
Yes, there is, yeah.
And I was wondering whether that can be used for other Artin groups which are not covered by your result, right? You know, so,
that's
because the two generator Artin groups, they're relatively simple, you know, and even if you don't have this geometric nice condition with the cut minus 1 sin, I mean, I don't know, I haven't thought about this, you know, seriously, but it would have.
So that's a very good idea, and we had completely missed this. So thanks for the suggestion.
I see.
Yeah.
Okay. So yeah, it may be for the future, right? You know?
Yes, maybe for the future. Yeah.
I see. Okay. Cool. Okay. All right. Very good. Are there any other questions or comments? Okay, let us thank Alex again. Thank you. So I'll stop the recording now.